All right, we're back rolling here. Momentum. All right, so go ahead in your notes. We're gonna spit a bunch of challenge questions at you guys. See if you guys remember these. Write the basic formula for momentum. Momentum equals what? Can you guys jot down that equation before I show it to you? All right. Yeah, spit you guys a bunch of challenge questions here. While you guys are writing that down, is momentum a scalar value or a vector value? Vector, right? Which means direction matter. So if you got two objects about to collide, left and right, going to the left and going to the right, is that negative momentum and positive momentum? Yep. Okay. Hey, what about last week when we were doing energy? Was energy a scalar or a vector? Energy was a scalar, right? So if someone's going left and someone's going right, could they both have positive kinetic energy? Yeah, both have positive kinetic energy. Right? But momentum, one's negative, one's positive, right? Also, I gave away I was going to ask you guys, what scenario are you looking for to apply this framework? You're looking for what kinds of scenarios? Collisions. There you go. Right. So did you guys write P equals mv? Right. Momentum is mass times velocity. Lowercase p, that's momentum. Right. So it's a vector value, so directions matter. That's what the arrow is for. That's a good habit just in general. If you put arrows above your vector variables to indicate that they're vectors, it's maybe not a bad idea too for forces, accelerations. You put these little arrows. Okay, okay, collision physics is involved in, right? It's conserved. Hey, so if there is a collision, then before and after the collision, all the momentum bits have to equate. Right? But don't forget to also include the negative and positive signs, all that, right? You guys got that? So you can't create or destroy momentum. Interesting. At least within a closed system. Right? Right. Conservation of momentum. So two objects headed toward each other. Pow. And then what happens? Well, depends. Kind of a material question, right? Like if they're balls of clay, maybe they stick together. Maybe if they're like Newton's cradle balls like these, maybe they bounce really nicely. Or maybe that kind of looks like half deflated tennis balls. Right? Regardless of which scenario that is, here, I'm covering up. I've got a gold box here that I'm covering up. Right? Can you guys write out the conservation of momentum equation that I've got covered up right there? See if you guys can do that from scratch. Right? Remember that's very conveniently for just collision all in one dimension. It looks like everything's just on the x-axis, just bounces back and forth on the x-axis. That's all AP is going to go. Right? Just one-dimensional collision. Can you write out the conservation of momentum equation for a collision like that? Yeah, we don't even know exactly what kind of collision that is. Is it Newton's cradle or clay balls or tennis balls? I don't know. Right, you guys got an equation? Right. Regardless of how bouncy those balls are, this gold box is always, always, always true. Right? So before and after the collision, momentum's conserved. Right? Okay, I'm saying sum of. So if I add up all the momentum bits, mass times velocity initial, mass velocity initial, for objects A and B, that's going to equal, and then mass times velocity for A and B added up after the collision. Right? Now my picture has, it looks like positive velocity for A and negative velocity for B. So maybe a positive number there and a negative number there. There's something there. Okay. Right, you guys got that? Okay. Now, remember, there's like a whole spectrum of possible collisions depending on how bouncy. So let's look at one extreme, which is called perfectly inelastic. It's perfectly inelastic. That means that the two objects are going to collide and do what? Stick. Yeah, collide and stick. Make one giant object and one final velocity. AP tends to prefer these types of collisions because the math is a lot more straightforward. Right? You guys see when we're going through this review. Right? Here, I'm covering up the answer. Can you guys write what I have covered up in your notes again before you see it? A little pop quiz right here. You know what that conservation of momentum looks like for that type of collision? I mean, for sure you're going to get asked this question probably multiple times. You're going to see this on the AP exam. Okay, you have to break out. Boom. Did you guys write that right there? Right. Yeah. Okay. So it starts out the same. Momentum before and after collision equates. Right? In fact, before collision is exactly the same as the general. Right. It's the same slot. Right. But after the collision, one giant mass, one common final velocity. You guys can do that, right? How about this? Right. What if you did energy accounting? So I say like, what is the kinetic energy before the collision? And let's say I get like 100 joules. I'm just making something up. 100 joules and let's move on. Right? And then they glide and stick, and then they're moving together, or maybe they come to a stop. What is the energy after the collision compared to before? Is it more than, less than, or the same as the original 100 joules?
The same. Wait, no.
Wait, maybe you can take a hint from if they possibly, it could come to a stop, right? But if you have MV to the right, MV to the left, and it just comes and stops, then how much kinetic energy? Zero, right? So kinetic energy has to go down, right? Okay. Yeah, okay, so that's a good general rule, right? Is that for any collision other than perfectly elastic, which is like the next slide, so we haven't hit, right? If it's not perfectly elastic, the kinetic energy score will go down. Okay. Oh, you might be if this was a free response question, you might be asked to explain that. It's like, hey, where'd the energy go? Did it just disappear from the universe? And you guys would say it went where? Deformation is a great answer. Yeah, permanent deformation. Right, these are clay balls, right? Versus, hey, look at this Newton's cradle here. This is like the opposite of that. It's like super bouncy, right? These balls are getting very deformed. Hardly at all, right? So those are really bouncy, but those are made of clay. Yeah, deformation, right? There's some kind of force times distance, some kind of work that goes into deforming the material, right? Sure. Okay, yeah. How about this? Could you turn this around in reverse? Do you guys remember grenade examples? Right, so what if you throw a grenade and it explodes into two parts? Isn't that just this collision exactly in reverse? Right? Could you just change what's initial and what's final? Could I say this is initial here, and this is two individual pieces final post collision, or sorry, explosion, I should say, post explosion, right?
Yeah.
Right. Now, if you did it that way, and then you did energy score, energy accounting, where would there be more energy? For the one grenade or for the two grenade parts that exploded? Yeah, two grenade parts exploded, right? But where did that energy come from? Was it created out of nothing? Did it come from the what? The chemical reaction, exactly, the explosion, right? Maybe it was like some gunpowder or whatever's in the grenade. Pow, that's where it came from. Right? Okay. So there's more energy here than there is here. Okay? Okay. But it doesn't violate the conservation of energy. Right, you guys ready for the next one? Next one? Right. So let's look at the other extreme, because this is one extreme kind of collision. They collide and stick together. Right. The other boundary condition, the other extreme, is called perfectly elastic. Right. Let's see if you guys can do is this green box. I've written a system of equations. There's two equations here. Can you guys write that system of equations in your notes? Go ahead. Give you guys a minute. Write that system of equations that I've got covered up in that green box. Right. How you can sort of mathematically define what makes perfectly elastic, which is pretty close to this Newton's cradle right here. Here, I wrote this stuff here for the video. Right. Newton's cradle. That's pretty close to what we're talking about. Pretty close to perfectly bouncy. Right? You guys, a little more time. Let's see if you guys can finish writing that system of equations that would define perfectly elastic. Perfectly elastic. All right, I think you guys are about wrapping that up. What two equations did you guys write? Did you guys say momentum's conserved? Although that's true for any type of collision, right? But also, what else is also conserved? Kinetic energy. Yeah, all the 1/2 mv squared bits. Right? Again, that's only true for perfectly bouncy, right? Perfectly elastic. That's what makes it perfectly elastic, right? Right? Guys got that? Right. Now, this gold box down here shows you the general solution, right? Regardless of the masses and the initial velocities of those objects, right? You'll always get that gold box, right? Right now, AP almost never asks perfectly elastic. I don't want to say never, but very rarely, right? Because you guys see how crazy the math would be, right? And if they do ask a question, they'll not really give you something too crazy. they wouldn't expect you to exactly solve this from scratch or like memorize that. Although I guess it wouldn't hurt to memorize it, but okay. But like one place I have seen them ask a question is like, I think there was a free response question where as one of the middle steps, they had like one ball like swing down and hit another ball. That was where it was like this. Right? There's one ball that came in and slammed another ball. They were equal masses, and the ball that being slammed into started at rest. So it looked like this. How? Right? And you guys see exactly what happened. One ball transferred all its momentum and energy exactly to the other ball if they're the same mass and one starts at rest. How? Right, you guys see that? Right. So yeah, that was like a middle step kind of application of this. That's usually about as deep as AP will go. Okay. Right. Or maybe you play off multiple choice answers and check this and say, okay, oh yeah, it would be elastic because energy is conserved, something like that. Okay. Okay. You guys can navigate that. All right. So let's put it all on a big old table. Here's a different kind of collisions. Or explosion. Hey, it's just perfectly inelastic in reverse. We just talked about that. Okay. Here's what it looks like. What's going on in terms of momentum and what's going on in terms of kinetic energy. So for every single one of these scenarios, perfectly bouncy, perfectly sticky, explosion in general, momentum's always conserved. Is that right? But kinetic energy, well, okay, that's a different story. Perfectly bouncy, kinetic energy conserved. Okay. In general, it goes down. For perfectly inelastic, has to go down. Right. And then for an explosion, it'll increase. But again, it comes from somewhere. You guys are saying, oh, maybe like a chemical reaction explosion comes from. Okay. All right. All right, guys, good. Okay. All right. Now, how could you quantify? Look, I forgot about this slide. All right, got to show you guys this one. All right. So, inelastic versus elastic. Say you had collisions with this bowling ball. What's going to get the bowling ball rolling faster? Suppose it's like the same mass moving at the same velocity. Right. Do you guys remember the elastic collision gets the bowling ball rolling faster? Okay. Here, let's do some numbers real fast. Suppose it was 1 kilogram going at 1 meter per second. If it sticks, that's transferring 1 unit of momentum. Okay. But if it bounces, boing, notice that it has to change direction. And if it's like nearly perfectly elastic, it could bounce up with up to twice the speed, right? Like if the bowling ball was like 1,000 times the mass, then this might come in at 1 meter per second and rebound with almost 1 meter per second the other way. So like up to twice the momentum transfer, right? Like as a boundary condition. Okay. All right, you guys get there? We got, you guys did this table with collision carts. See, in general, they were boing, bouncing off each other. You guys had somewhere tape magnets where they stick together. So you're inelastic. You could, here's a version of this too, where you can have them starting together. You can push a lever, no, bounce off it, or like explode. We didn't quite do that one, but it's something you could do it here. Okay. Oh, here's how you could quantify how bouncy is a collision, right? Now, AP is not going to ask this. So this is just extra information for this class. You might get it in college and something like that, right? So the pre-collision and post-collision difference in velocities. So do difference post compared to difference pre, make it an absolute value. Okay, great. Actually, you guys did do this lab. I had you guys do this, where you let the ball bounce off the floor, and between the ball and the floor, it's like a ball and a tile floor. There's some associated coefficient of restitution. Right? I guess I think it would be fair for AP to ask this, but they would have to tell you the definition of coefficient of restitution. Like they would definitely have to give that to you. Okay? But they say, how would you figure it out given that knowledge that we're giving to you right now? Okay. Okay. So you say, well, the Earth that this is bouncing off is basically not moving. So I mean, compared to the object, relative to the object. So we're going to like subtract 0 speed from that. Okay, so that goes away. Okay. Then what is the crash speed? Well, it's square root 2gh playing off the drop height. And what is the rebound speed from the floor? Well, it's square root 2gh playing off the rebound height. Now, I would derive that. And that comes from conservation of energy. You guys remember that? Like Galileo drops the ball, how fast? Right? That's where that comes from. Right? And then that's what we're comparing. The 2g cancels, and that's why it ends up very simply boiling down to this. Okay? I think you guys should be able to derive this from scratch. Right? Again, I think it would be just fair enough. Like if they told you this and it said, okay, using this can you figure out what is the coefficient of restitution? Say if you drop it from 100 centimeters and it rebounds to 70 centimeters, can you figure that out? And this is always the answer to that question. Okay. Right. How bouncy is the ball if the tile floor? Oh, here's the lab table you guys did for that lab. Okay. Oh, everybody good so far? Okay. Okay. Ooh, closed and open systems. So here's something that keeps coming back over and over. AP really cares a lot about this. And you guys see different perspectives of what makes something closed or open. So going back over the last few weeks, one definition of closed or open is there an external force on the object or the system or not? If there's no external force, it could be closed. If there is an external force, it could be open. Okay. Last week, we were thinking in energy and work terms. Okay, that's something to do with force times distance. Okay, so if there's no energy entering or leaving the system, that could be closed. And if there is energy entering or leaving, that's to say if there's work on the system or work done by the system, then that could be open. Right? But what you guys are looking at right here is like a third perspective, right? Which is momentum entering or leaving. Guys, what's another term for change of momentum? What's that called? Starts with an I. Impulse. That's what I'm looking for. Impulse. Right? Like a transfer of momentum. Right? Okay, so there's still some kind of external force, but now it's multiplied by some time interval, right? Force times time. Right? Okay. Right. So you guys go with closed and open systems, right? All right. This next poster. Ooh. Impulse. Impulse. Right. Guys, write down on your paper everything you remember about impulse. Okay. I've got a graph I'm covering up. I've got some equations I'm covering up. Right. Write down in your notes everything you remember about impulse, because you're gonna get multiple questions about impulse on the AP exam. What are the axes on that graph? What property that graph represents? A transfer momentum. Okay, you guys see my vertical axis is force in newtons. Right? So you get that. Right? Your bingo free space. Right? And then when you make equations out of this, what do those equations look like? I think maybe two equations I can push together in one line, maybe. I think on this poster. All right. Let's see, good graphs, good equations. Yeah. Okay. I think you guys are getting this. You guys remember this? All right. So on the AP exam, you're gonna get force versus time graphs, and whenever you see a force versus time graph, expect the question of something to do with like impulse, momentum transfer, right? Which oftentimes goes hand in hand with a collision, right? Would make sense, right? That's why my classic example here is the bat hits a ball, right? So area under force versus time, right? Now, it could be a constant force for some time. That's okay. In which case you get a rectangle shape, right? But more often than not, you'll tend to see these triangle type shapes, right? And it makes sense if you think about like videoing this bat hitting this ball and then putting it into slow motion. So at some point, the bat makes contact with the ball, that pushes more and more and more against the ball, then the ball starts to rebound, and finally the ball leaves the bat right here. Right? So it's like a process that maybe takes like a tiny fraction of a second, right? Something like that, right? So, but do you guys see that the area of this triangle and the area of that rectangle? I'm trying to show that they could be like the same, except, right? Where in this case, if it's a true triangle, then the maximum force would be double the average force, like that, right? And here's the equations that go along with this. So delta P, change in momentum, right? It's called impulse, right? And here's like two equations I pushed into one line. So you could do mass and change of velocity. So this ball has a constant mass, but it's changing its velocity. Now, careful about that, because if it's thrown in towards the left and it's hit back towards the right, okay, you got to be able to handle negative signs. Let's see if you guys can do that. Suppose the pitcher throws the ball at like 50 meters per second to the left, and the batter hits it 60 meters per second to the right. Guys, what is the difference between 50 to the left and 60 to the right? And don't say 10. Huh? 110. Right? Because you have to do 60 meters per second minus negative 50 meters per second, right? Which, oh, by the way, that's really fast. I just realized that's like Nolan Ryan's speed, but just gonna, right? Yeah. So a difference between a positive and a negative makes the number really big. Okay? You say here. Right. And then the other perspective could be force times time. Now here I put average force times time interval, which again gives you like a rectangle shape, right? But if you have a variable force, you guys can say it would just be the area under the curve. If you wanted more like math type notation, how many of you guys are calculus, right? You guys are probably done integrals by now, right? Integrals, right? You guys do see that would be an integral, right? Just do integral f dot dt is what that would be, right? And that's for that triangle, right? You guys got it? Right. One last little detail I went through. I don't think this is probably going to come up in the exam, but who knows, right? Is you could modify this a little bit. What if you have a non-constant mass but a constant velocity? Could you do that? Right? Which is not exactly what this shows. It's kind of like shuffling that delta over to the m. Right? What if you have a conveyor belt that's moving on, and there's like a line of bottles, and they're filling up these bottles like with water, right? And the conveyor belt moves at a constant speed, but we're changing the mass that's on the conveyor belt because we're filling all these bottles with water. We're adding mass. Okay, that'd be like a changing mass at some constant speed, and then you need like a constant force from the motor moving it along, right? Could be that too, right? So a little bit different take on that. Ballistic pendulum. Okay. So remind you guys of this scenario. This is a really classic physics setup. If you take physics in college, you're gonna get asked this question. Okay? Is you fire a bullet into a block and the whole pendulum swings up to some height change, right? And there's different questions to go on this, right? But usually the question is, how fast was the bullet fired given everything else? Okay, right? Oh, and this is basically a two-part problem. Right? So you guys see I'm covering up a green box and a gold box. You guys see that? Right. So let's go through step by step. Now, if the question is what's the firing speed of the bullet, then chronologically is the first thing to happen. So looks like we're solving this back in time. I mean, you'd have to be given something to do with the height change, something like that, right? Right. And if you're solving this back in time, then the pendulum swinging up to some height, what framework in physics are you using to solve that? It's not conservation of momentum. It's conservation of what? Energy, right? Right. So there's some post-collision velocity of the bullet embedded in the block with kinetic energy, swing up some height that's all potential energy at the max height. Is that true? Right. So could that be like here? Show you guys that. Something like this, right? Right. 1/2 m squared turns into mgh. The m cancels. Bullet plus block. Yeah. And let's look at that. Square root GGH. Right. So the kickoff speed again, like this is post collision. Right. Oh, turning into some height. Yeah, that speed is square root GGH. Right. You guys remember that? Right. Let's throw in an extra detail here because you might have to navigate this. What if you are not exactly explicitly given that height change, but you are given L and theta? Can you guys figure out what is H based on L and theta? What is that relationship? What do you guys think of that? See if I can dig this up from last week's. You guys remember that from a few days ago? Right. You guys remember this height change is L times 1 minus cosine theta? Right? Could you substitute for that H? You could do L 1 minus cosine theta. You could do, right? All right. And then, I'm still covering up this gold box though. Guys, what's underneath this gold box? What's the first line? Momentum is conserved. Right. I'm referring to, okay, so we're stepping back in time again. So this is what happened last. This is the step before chronologically, right? Is the bullet embedded itself in the block, right? Now that you cannot use conservation of energy because there was so much work that was done deforming the block. You guys did deformation earlier, right? There's definitely a perfectly inelastic collision. Right? However much kinetic energy was in the bullet, well, there was a lot of work that was done, like pushing the wood fibers out of the way. I bet the wood heated up a little bit, thermal energy, right? And it's extremely hard to account for that, right? But momentum was for sure conserved during that inelastic collision, wasn't it? Right? Is that true? Right? Oh, so good. Okay. Right, so then, would you guys say mass times velocity of the bullet? That was like the source of the momentum. Right here it is firing, has got some mv. Boom, that's that. Right? And then it embeds itself in the block. So there's a giant mass, block plus bullet, moving at some post collision velocity. How fast? Square root 2gh. Right? Divide by the mass of the bullet, you get, there's the firing speed of the bullet. In terms of the mass of the block, mass of the bullet, gravity field of the planet, and the height change. Don't forget to it would be reasonable for someone to ask you, what is the height change based on L and theta? And you guys remember this geometry from last week. Okay, you guys can do that. Okay, guys good? Okay. Here's the last poster, and this one I don't think AP is going to ask you because I've never seen AP ask this question. Is what about a two-dimensional collision? So if you have billiard balls, it's like boink, maybe this red ball knocked this green ball, right? Or you could turn this around backwards, right? What if there's two cars that's kind of like towards an intersection, but there's like a pole between them, and they don't see each other. They stick together and move together, right? It's kind of that in reverse, right? Whatever scenario, I've got this Cartesian plane x, y. Right? Momentum is conserved in each direction. Right? So regardless of what kind of collision you're working with, you can say the momentum in the x direction is conserved. The momentum in the y direction is also conserved. So in my case, maybe I've got a red billiard ball bouncing in off this green billiard ball. There's definitely some rightward momentum that's conserved before and after. Right? But however, whatever momentum up mass times velocity, like this vertical component, it exactly cancels out with this vertical component of the green one going down, because it was only ever zero coming in, so it's only ever zero after collision too. Right? Zero vertical momentum here, zero vertical momentum here. Okay, right? Yeah, you might say that one in college, right? But that is all my momentum posters, right? And just in time because we got 30 seconds to the bell. Right, so can you guys turn in that scored FRQ, scored now 12, and then tomorrow you guys going to bring laptop winner.